Jordi talked about it is actually an important problem to how to infer human values, and it is actually a quite hard problem for several reasons that I'm going to mention. My talk is actually going to be about an idea or a method that could be used for inferring human values, which could be used for designing safe AGIs. So whenever we are talking about intelligence, there actually needs to be some goals. And the basic intuition is that you have an agent A and an agent B, and you want to say that the agent A is more intelligent than the agent B. So if you want to say that, you actually need to have a criteria to judge the performances of those agents. And whenever you have a criteria, you could put the criteria as goals or values or rewards. So to talk about intelligence, we need to have some goals. And this kind of implies that whatever the architecture of an AGI is, it will likely have an explicit value function. And even if you could actually create an AGI agent which doesn't have an explicit value function, I would argue that you could simulate that AGI agent with a reinforcement learner which has a specific utility function. But this is a whole new argument. Since it is likely that an AGI will have an utility function, it is important to kind of align the utility function of AGIs with human values so that the AGI will actually optimize what we value. So the problem that I'm going to address is how can an AGI learn what humans value, and this has been also dubbed as the value learning problem. This actually turns out to be a quite hard problem for several reasons, because humans have complex value systems. That is, our values are not like composed of one or two features. It likely has a long list of features. And it is also shown that when you ask a human what do you value, actually they are not able to tell you what they value, which is not surprising. And even if they could tell you, I value freedom, liberty, autonomy, etc., those are fuzzy English terms, right? They don't have like a precise formal meaning. So it seems as though kind of crafting utility functions or value functions for AGIs by hand or by surveying is impractical. So what we can do is we can use something like machine learning, supervised learning, in which we learn a utility function which maps perceptions or perception histories to utilities, real-valued utilities, and there are different ways to potentially do this. So we can show humans an outcome, like a video or an image, and ask them to rate the outcomes, or we can perhaps model humans and ask modeled humans to assign utility values, or we can try to find the utility indicators such as the total number of smiles or the total number of neuromodulator levels in the brain, such as dopamine. And this is not an exhaustive list. There are other ways to do this, but it seems as though these methods have serious shortcomings as well. So for example, if we ask humans to rate outcomes, they might actually prefer not to reveal their true preferences to signal certain values. Eliezer Yudkowsky discusses in his coherent extrapolated volition paper that what humans value would be different if they knew more and if they were smarter. So it might not be a very good idea to basically ask humans what they value today. And if you said we want the AGI to find to optimize the total neuromodulator levels in the brain, say total dopamine, it will also likely not be a good solution, because, for example, if we gave dopamine, then the AGI would probably try to make everyone drug addicts, right? Perhaps a more complex set of utility indicators could be used, but it seems like it's also not a very good way to tackle. So instead of using a method such as supervised learning, we can attempt to directly estimate human values without requiring humans to reveal their preferences. And I'm going to present a method to achieve this. But before that, I want to take a step back and kind of reason about the general agent environment interaction schema. So we assume that there's an agent that takes an action and perhaps modifies the environment and then makes a perception. And here we know that if we give a utility function to the agent such that the function will map perceptions to real values, the agent can learn a good policy or an optimal policy using methods such as reinforcement learning. There is this rather recent method called inverse reinforcement learning, which in a way solves the inverse problem of reinforcement learning. And we can think of it as finding the reward function of an agent that you only see the policy of or samples from the policy. So sampling from policy would mean we see the behavior of an agent. We have no idea what the agent finds rewarding, and we are trying to find what the agent actually value. And inverse reinforcement learning is heavily used in robotics, and I'm going to talk about why it is used in robotics in the next slide. And it is also suggested that inverse reinforcement learning might be used to learn human values, but this is actually not possible with current state-of-the-art inverse reinforcement learning methods, because when we look at those methods, they have a whole bunch of different assumptions. So the environment is assumed to be stationary, fully observable, known, Markovian, and the policy is assumed to be stationary and optimal, and especially this optimality criteria is super troublesome because we cannot assume humans to be optimal. There is a whole bunch of literature that shows that we are far from optimal, especially in high-level decision-making tasks. And the reason robotics people can get away with making this assumption is that in robotics you can assume that a human does like a certain behavior, such as manipulation or walking optimally, and you can try to basically get the same behavior using robots. So in like motor control, it might perhaps be okay to assume optimality, but for most of the things, humans are far from being optimal. And the reward functions are usually assumed to be stationary, which is also not the case with us. So I want to address these limitations of inverse reinforcement learning methods by devising a very general method for inferring human values. And here, if we assume that if the agent is actually a biological agent, such as a human, we know that the rewards are computed in the agent. So it is like black box. We don't know what's going on in the brain. We just see the actions and perceptions. And when we look at the brain, it seems as though the rewards are computed by several regions, mostly included in the basal ganglia. And it seems as though basal ganglia gets inputs from the cortex and then makes a computation and then outputs signals to the cortex. And if we assume that this reward mechanism is an isolated mechanism, which is a simplification, of course, but if we assume this reward mechanism is isolated, then we would be able to basically model the reward mechanism. And for those of you who are familiar with AGI, I use basically the same schema. So I propose that we can model an agent with two different mechanisms. The one is the reward mechanism, and the other one is the decision mechanism. And what reward mechanism does is that it computes rewards from observations, and the decision mechanism takes into account both the rewards and the observations and computes an action. And these are infinite tapes, and the agent and the environment interact, and the environment can be basically any reference machine. It doesn't matter for my formulation. So here we assume that we actually can see the action tape and the observation tape, and what we want to find is the most likely program of the reward mechanism, or basically a probability distribution over different reward mechanisms. And the way to do is to use Solomonov induction. I think most of you know, I'm not going to get into details, but the important part is that it loops over programs that are valid with the observation, or like what we want to see, and gives them this weight. And if we assume that if we can define a joint prior over different programs, and if we assume that they are independent, we can actually define a joint prior such as this, and then we can find basically the probability, or like we would need normalize, but we can find the probability of a reward mechanism given an action and observation history using this equation. And what this does is basically it loops over different decision programs, and it keeps the ones that are valid and gives this weight to the PR-PD pairs. And of course, we would also need to have another loop which loops over different reward programs. This solves basically the problem of inverse reinforcement learning in a very general sense. Of course, this is not computable, but we can set a limit on the length of the PRs and PDs, because we humans, almost done. We humans have kind of limited computation ability, so we don't need to loop over all programs, and we can also use a different prior to kind of handle non-halting problems such as Schmidt-Huber's speed prior to make this computable. And this, since there are like very few assumptions here, this could actually be used for inferring values of humans in arbitrary domains. And how it could be done is that, of course, this is super simplistic, is that we can pick a number of humans and capture inputs and outputs, which is actually quite hard thing to do in real life. You would need to put them like something like an Iron Man suit to capture all the inputs, outputs, and then estimate the values of the humans using a method such as the one I showed. And then we need to do some pre-processing, and this is necessary because we humans value eating, and we also value if other people eat, but the robot shouldn't value eating. So, but it should value that other people's eat. So there's like some pre-processing that is necessary to map human values to robot values. And then we would need to combine the values, and there are different ways to combine. And then we could give the estimated values to an AGI as its utility function, and perhaps it would optimize actually for our values or utilities, but this is not complete. It's kind of a early stage. And you can find the references when it's uploaded. Thank you very much for your attention.